If you really want to get a programming language, you can't just memorize the rules and the syntax. You've got to understand why it was born, what was the big problem it was trying to solve. And the story of Java, well, it's pretty much a fantastic tour through the entire history of modern computing. So that brings up a really basic question, right? I mean, we already have hundreds of programming languages out there. So why on earth do we keep inventing more? What's driving this constant need to create something new? Well, it really boils down to two big things. First, the world around us is always changing. Just think about it. The internet pops up, then suddenly everyone has a smartphone in their pocket. The old tools just can't keep up. And second, we as programmers just get smarter. We figure out better, more elegant ways to build software. So this whole story is really about problems and the clever solutions that come next. Okay, so let's rewind the clock. Our story really kicks off in an era of, well, programming chaos. Before we could even dream of building the apps we use every single day, we had this huge fundamental problem to solve. Code was becoming a total mess, and every choice felt like a bad compromise. Back in the early days, if you were a programmer, you were always stuck between a rock and a hard place. You could pick a language that was easy to learn, or one that was super powerful. You could have one that was safe and held your hand, or one that was blazingly fast. You can never ever have it all in one package. It was always a frustrating trade-off. And all this led to this infamous thing called spaghetti code. And it's exactly what it sounds like. Imagine trying to follow a single noodle in a giant bowl of spaghetti. That's what reading these programs was like. They jump from here to there with no clear structure. For a tiny program, maybe that's okay. But as programs got bigger, it was an absolute nightmare to fix or even just to understand. And then along came the solution, the C language. C was a total game changer. Why? Because it finally brought these warring ideas together. It was powerful and efficient, but it also introduced a clear, understandable structure. And maybe the most important part? It was built by programmers for programmers. It wasn't some academic theory. It was a tool for getting real work done. And man, it changed everything. But here's the funny thing about great solutions, right? They often create new, even bigger problems. C was so successful that it allowed programmers to build applications that were way, way bigger than before. And suddenly, we hit a new wall. The programs got so massive that even C's structured approach just wasn't enough to keep the complexity in check. It was a really logical progression when you think about it. C let us build software skyscrapers, but we were still trying to design them on the back of a napkin. We hit this complexity ceiling, a point where a single human brain literally could not hold the entire program in their head anymore. We needed a new way to think, a new way to organize. And that new approach, that led to the next big step in the evolution of C++. So what was the big idea in C++? It was a concept called object-oriented programming, or OOP for short. Now, let's not get lost in the weeds here, but the basic idea is just genius. It's about grouping your data and the code that works with that data into these neat little self-contained packages called objects. Think of them like super-powered Lego bricks. It was a revolutionary way to organize these massive, sprawling programs and finally make them manageable. For a while there, C++ was king. It really felt like we'd finally cracked it, that this was the language to solve our complexity problems. But then, something happened. A force of nature emerged that nobody really saw coming, and it was about to change the world and create a problem on a completely different scale. And that, of course, was the internet. Okay, and this part of the story is where the timing is just, it's incredible. Picture this. It's 1991. A small, secret team at Sun Microsystems starts a project called Oak. Their goal? Create a language that could run on all sorts of different devices. TVs, remote controls, you name it. Then, just a couple of years later, bam, the World Wide Web absolutely explodes in popularity. And what does the web need more than anything? A language that can run on any computer anywhere. It was the perfect storm. The solution was literally being built just as the world's biggest problem was emerging. So let's break down the challenge the internet created. It was really two huge problems rolled into one. First, you've got portability. How in the world do you write a single piece of software that can run perfectly on a Mac, a Windows PC, a Linux server, on everything? And second, and this is a big one, security. How can you download and run code from some random website without letting it take over your computer and steal all your files? These were massive, massive hurdles. And Java's answer to this was just so elegant. It was captured in what has to be one of the greatest marketing slogans in tech history. Write once, run anywhere. I mean, that was the dream, the absolute holy grail for every developer. And the magic powering this incredible promise was a piece of technology called the Java Virtual Machine. So how did they pull it off? How could one single innovation solve both of these massive, seemingly unrelated problems at the exact same time? Okay, so here's the first part of the trick. When you compile a Java program, it doesn't create machine code for your specific computer like a typical program. Instead, it creates something in the middle, an intermediate language called bytecode. The best way to think of it is as instructions for a computer that doesn't physically exist. It's code for a virtual computer. And that brings us to the second, crucial piece of the puzzle, the Java Virtual Machine, or JVM. Now, the JVM is a real program, and it's installed on your actual computer. There's a JVM for Mac, one for Windows, one for Linux. And its only job, its entire purpose in life, is to take that universal bytecode and translate it in real time for the specific machine it's running on. It's literally a universal translator that sits on every computer. And that is the magic right there. You write your code once, you compile it to this universal bytecode just once, and then you can send that single file to any computer in the world as long as it has a JVM. The JVM handles the translation, boom, that's portability solved. And because the JVM is the middleman, it acts like a security guard. It puts the code in a secure sandbox where it can't do anything malicious. Boom, security solved. 2 birds with 1 brilliant stone. It was genius. But look, the story doesn't end in 1995. Not even close. In the world of technology, if you're not moving forward, you're dying. And the reason Java is still an absolute powerhouse today, decades later, is because it never, ever stopped evolving. It kept finding new problems to solve. And you can see it right here. Just look at some of the major milestones. In 2004, it added generics, a huge deal for writing safer, cleaner code. Fast forward to 2014, it embraces modern functional programming with Lambda expressions, and it just keeps going. More recently, we've gotten things like modules to help organize gigantic apps and virtual threads, which is a massive leap forward for handling tons of users at once. This language just refuses to stand still. And get this, the pace of innovation has actually sped up a lot. Today, Java has a major new release packed with features every 6 months. Just 6 months. That's an incredible pace, and it means the language can react and adapt to new trends in the tech world super fast. You know, it's funny to look back at the original buzzwords the creators of Java used to describe their goals. Simple, secure, portable, robust. But what's really amazing is how well they still describe the language today. They weren't just marketing fluff. They built a foundation that was so solid, it's still what defines Java decades later. That is some serious foresight. So when you put it all together, the story of C, then C++, and then Java, you see this beautiful, clear pattern. The really great, enduring programming languages aren't just academic exercises created in a lab. They are tools forged in the fire of the biggest, most pressing technological challenges of their era. Which leaves us with one last really big question for the future, doesn't it? As we look ahead, we're dealing with a whole new set of mind-bending challenges. We're talking about massive-scale AI, planet-spanning cloud systems, even quantum computing. So what's the next huge problem that's going to demand a completely new way of thinking, a brand new way to program? And what will that next revolutionary language, the next Java, even look like?